as they wanted. And by getting smaller and smaller size elements, they're approaching the limit of integration, meaning they're getting a more accurate, a more exact value, especially if they're doing it using a numerical approach. So in the CAD systems, what we have are the ability to simply pull down a menu, go over to the menu, select a simple click, and it gives us generally a dialog box. The dialog box requires that we identify which part or parts we're going to be doing master properties on. It allows us to kind of save this information off to a spreadsheet. It allows us to kind of manipulate or modify the accuracy. And when you play with the accuracy, you'll find out that on the simple parts that we're doing, messing around with the accuracy has nothing to do with much of anything. But if you were at Boeing and you were trying to get the match property of, say, a complete wing that has tens of thousands of parts in that single wing, leaving it ratcheted up on the most accurate setting is going to take quite a while for it to come back and calculate a mass property. So what is it that it actually gives to us? And I skipped one. So here are kind of the calculations that that generally are handed to us by the CAD system. It starts out by telling us what units it thinks it's operating in, and so generally, if I can make my mouse work, why is that not working on this desk? So, wow. Mouse pad. Technical difficulties on the mouse. Well, so generally it's going to tell us what kind of, what units we're actually working in, and that's just typically a reminder to us so that we're checking to say, did we enter the density in the correct units, or did we enter an inappropriate, we messed up our units as we entered some of this stuff. After that, it kind of comes down. It can tell us what the density of the material is. In this case, it says 0.097. And so that should be the density of aluminum entered in inches, in cubic inches. It gives us an area, and that area is considered kind of the wetted area, or the area that could be painted. How much paint, how much square inches of paint would be applied to this. After that, it talks about volume, it talks about the mass, and then it drops in and starts giving us information like centroid, first moment of inertia, first moment of mass, moment of inertia. The moment of inertia oftentimes is given to us a number of different ways. It's given to us based on where the working coordinate system is. So that's the first one. It's in relationship to kind of the current XYZ 0. The next one, when it says centroidal, it's giving us the moments of inertia about the centroid of the part. The spherical value that it gives there for the moments of inertia, there's basically a theory that says you can compare one object to another by how it relates to the spherical moment of inertia. And so you're basically back calculating a radius of a sphere and comparing it to the radius of another sphere. And so the objects may look very different, but you can compare them in terms of how do they look if you were to have similar spheres sitting side by side with each other. And then on the right-hand column, it begins dropping down through the products of inertia, the principal axes, the radius of gyration, and then at the very bottom it gives principal axes for this particular part. And so there's quite a bit of information that's actually provided by the mass properties. And in my professional life at Boeing and Lockheed, the CAD systems really did not have very accurate mass properties because they were doing it with just summation of small elements. Then this was improved significantly in the mid-'80s and into the '90s. They started greatly enhancing and improving the calculations, the accuracy of this. Working with Pratt & Whitney back in 2000 when I was on a sabbatical, Pratt & Whitney regularly checks the mass properties of almost every component that is put into the engine, and certainly of every stage inside of the engine. They will build up an assembly and they'll check the products of inertia for that given assembly to make sure that the products of inertia are as close to zero, if not zero, to make sure that they don't get any imbalance. In real life, you can't ever make anything as accurate as what the CAD system predicts. And so what they typically do is once they get a stage built, they do the exact same thing that the tire shop does. They spin the rotor along with all the blades on it, and they figure out the out of balance, and they add weight or remove weight to try and bring that disc into balance so that it doesn't have any of the wobble or vibrations that it would introduce. We are also asking that as a team that you think seriously about doing some assembly mass properties. The CAD systems do that in the same way. Instead of selecting a single part, you select an assembly. And if the assembly has all of the material properties assigned to each component, then it can very accurately predict or estimate what the mass properties are and where all of the principal axes and the products, where they all fall. And so this is a bit of an eye chart. It's the same information. It's just given for the entire product. And so using that information and looking at that information in relationship to an overall assembly can kind of guide you in improving or changing, modifying a design to make it better. If you modify the design too much, which kind of happens in real life out in industry, if you remove material, if you kind of shave off portions of a body, you need to then start, and you get the mass properties where you like them, You then need to think about redoing the finite element model to make sure that you haven't weakened the structure or the assembly to a point that it can't perform. And so if you're trying to reduce weight or take weight out of a part or an assembly, and you change a thickness, it's okay to do that, but doing that without rerunning the finite element is probably not the best idea, because you may have weakened that component to the point that it falls below its safety factor, it falls below its strength requirements, and you're going to have lots of recalls where you're replacing parts at a very high cost to the company. And so as you work on your project and move forward with your project, we would like you to, as a team, think about components, individual components that you can kind of do mass properties on and compare them to maybe the actual part that you have in hand that you can weigh and kind of calculate a comparison between. We would like you to also think about key assemblies that you may want to do mass properties on, and again, check that or compare it to the actual assembly, and then make sure that you loop back to do a finite element analysis if you're bringing the weight considerably lower. So now what we need to do is talk about how the calculations are really done inside of the CAD system. Before kind of jumping into this, I want to try an experiment, and I'm going to call on some of my students back at BYU, and we're going to see how well this works. Is Mark Banner in the class?
He's at a job interview.
He's at an interview.
Is Mark back at BYU?
He's at an interview right now.
He's what?
He's at an interview.
Oh, so I'll have to fail him, I guess, for today.
Fail it.
Don't tell him that. Is Chris there?
Yep.
Hey, Chris.
Yeah.
What is your understanding if I was to say, what is the bounding box of that part? What would you think I was talking about?
I would think that you take like the outermost edges of that part, and then you create a box to surround that you could then subtract areas from to get the total, is what I would think.
Okay. So what if I were to then say, well, what is the largest inscribed box? Or the largest inscribed volume? Maybe it's not a box. A box just means a volume. What's the largest inscribed volume?
The two guesses I would make, the first guess I'd make is it's the largest negative volume that exists within that bounding box. And then the second guess, if that wasn't right, would be that it's the biggest positive kind of area that's separated. But I think it'd be like the first guess.
Okay. So let's assume that the part that you were modeling, the part was a sphere, and I asked you for the largest bounding volume, and the volume that we want to work with is a box. So what is the largest bounding volume for that sphere? What would that be?
I guess you would take the diameter of that as the side of a cube, and I'd say the bounding would be then that side, cube. Would be the bounding volume.
Okay, and what would be the largest inscribed box for that?
Trying to get the best equation that you'd get there.